In our introduction, we suggested that the most mathematically precise way to define a fraction is as a point on a number line. Focusing on fractions as numbers helps students understand that the mathematical operations that we do with them are identical to those that they know already for whole numbers. But fractions are more powerful than whole numbers because they can represent ideas that we cannot count. For students who have only thought of numbers as a means to count things, the idea of a fraction is a big conceptual leap. Now numbers represent part of something. They may also represent ratios. In fact, the word fraction comes from the Latin word fractus, which means broken. The idea here is that we can break up something that we formerly thought of as a single unit into parts of that unit or other definitions of what a unit is. We will define fractions using a number line. From work in the first or second grade, students should be familiar with the number line that represents the whole numbers as evenly spaced tick marks on a horizontal line. Let's review where this idea came from. We start with a horizontal line and choose some arbitrary point on it, usually to the left, and call it 0. At that point, we pick a second point to the right of the 0, and by labeling this point 1, we have defined a unit. Notice two ideas here that are subtly different. We've defined a length of 1 unit, and we've also defined a point on the number line that is at 1 unit. This point represents the more abstract idea of the number 1. This special segment on the number line is called the unit segment. That's the segment from 0 to 1, and we represent it using the notation square brackets 0, 1, close square brackets. Now the remaining whole numbers can be defined. They are the locations on the number line that fall at full multiples of the unit segment. So for example, if we move two of these distances, the unit segment distances from 0, we get to the whole number 2. If we move 3 lengths, we get to the whole number 3, and so on. Incidentally, one can move to the left of 0 in this same manner and define negative values and the integers. Notice now that any segment that has a length that is an integral number of unit segments, say from A to B, this length is a multiple of the unit segment. This is an idea that we use when we add and subtract numbers on a number line. We should stress to students that the physical length of each segment in the number line is unimportant. 1 unit is defined by whatever distance is chosen from 0 to 1. By extension, we can see that 1 unit will be the distance between any two whole numbers on the number line. So let's move on to fractions. One can imagine breaking the unit segment into, say, 5 equal parts. Let's focus on this first part here. Again, two ideas are defined. One is the location of that point, and the other is the length of the segment. Clearly we can't call that location 1. We've already defined that as our segment. So we have new notation that we need to bring in, and that is the notation 1/5. We will use that name to define that point on the number line, and it also defines, therefore, this segment, the length of that segment, just as we did with the whole numbers. And now, in a similar way, we can look at the full multiples of this distance and give them names that represent multiples of a 5th. We'll call this position here 2 of those, or 2/5. Over here we have 3/5, 4/5, 5/5, and so on. And in fact, we can keep going by continuing our subdivisions of 5 parts for every whole unit and have fractions such as 6/5 and 7/5 and so forth. And 10/5. Notice that using this notation, we've actually defined new names for numbers that we already had. For example, we now have 5/5 as another name for the whole number 1. Likewise, we have 10/5 as a new name for the number 2. We can take it one step further. Don't forget 0/5, another name for 0. So in this example, we had broken the unit segment down into 5 equal parts, and we called that segment 1/5. But there was nothing magic about choosing 1/5. In fact, let's suppose that we break the unit segment down into n parts. I've included a little squiggly mark to show that I'm not sure how many segments fit between 0 and 1, but if I choose to break the unit segment into n parts, then the notation that I'll use to represent the first mark, the first segment, is 1/n. If I double that length, I have 2/n, which represents the next point. I can triple that length and get to 3/n, and so forth. Now at this point I don't know how many segments are located in this break, but I do know that by the time I get to 1, I have to have created n segments, each of which is 1/n in length. I can continue going. This would be the next segment, one more multiple of 1/n. That would be called n plus 1/n, n plus 2/n, and so forth, all the way till I get up to the number 2. And by the time I get to 2, I will have had n segments here and another n segments there. That's 2n segments, and each of those segments is a 1/n, so I'll have 2n/n segments by the time I get to there, and this would be another name for the number 2. So from this, we can generalize the equivalence of whole numbers and fractions if we introduce one more symbol. If we let m be some whole number, any whole number, then m times n will be the number of segments in n whole numbers. Here's one whole number, two whole numbers. If we go up to m of those, each of them has n segments. We'll have m times n segments, and each of those segments is a 1/n segment, and we get that this expression, m times n/n, will be the same as the whole number m. Let's highlight that one because it's an important result. There we are. And probably the most common use of this fact is when we notice that 1 is equal to n/n. Any whole number over itself as a fraction represents the whole number 1. I should point out that for the purposes of this discussion, we have limited ourselves and should be aware that we're talking about n greater than 0. So in short, a fraction is a number that is a multiple of the number 1/n that we define by breaking the unit segment into n equal parts. So you may notice that by breaking the unit segment from 0 to 1 into smaller and smaller and smaller subsegments, we can fit an infinite number of numbers between 0 and 1. So you may be tempted to conclude that there are no other numbers except for whole numbers and fractions. However, the Pythagoreans, you remember the Pythagorean theorem named after Pythagoras? They knew in the 5th century BCE that the length of the diagonal of the square, whose sides was 1, was a number that could not be written as a fraction. These are called irrational numbers, and our study of them will have to wait for another day. One of the things that students need to know how to do is to locate fractions on a number line. For simple fractions, such as 3/4, we can proceed from the definition. We simply break the unit segment into 4 equal parts. We identify the length of 1/4, and then we move 3 times that length from 0 to the right, and we arrive at the location that represents 3/4. Again, we have the location 3/4 here on the number line, and we also have the length 3/4, which is the length of the segment from 0 to 3/4. In general, for the fraction a over b, we break the unit segment into equally spaced parts, b of them, equal hopefully, and there are b of these parts, and we identify the length 1 over b, which is the distance from 0 to the first segment, and we move a of those segments, 1, 2, 3, a of those segments, whatever that is, and we come to the location a over b. However, there are times when this strategy is not so simple. Take, for example, the fraction 17/36. It would be rather difficult to break the unit segment into 36 segments and count from the left 17 of those. So one strategy is to compare the fraction we're trying to place to what we call benchmark fractions. We look at 17/36 and we recognize that 17 is about half of 36, and therefore the number 17/36 should be somewhere close to the number 1/2. Now we just need to know, is it smaller or larger than 1/2, and by how much? From the definition of fractions, we know that 36 involves breaking the unit segment into 36 equal parts, which is a bunch of them, equal, of course, and that if we move 18 of those 36, we would end up at a half. So 1/2 would be the same as 18/36. Now we can compare our numerator, 17, with 18, and see that 17/36 is really moving only 17/36, a little bit less than 18/36, from 0. And so 17/36 is going to be located slightly to the left of 1/2. Now, slightly in mathematics is not sufficient. We need to be more precise. So exactly how far is that distance right there? Well, we know it's 1/36. This is called locating fractions using a benchmark. 1/2 is the benchmark fraction, a common one that all students should know. Notice that in this case, our benchmark fraction, 18/36, had the same denominator as the fraction that we were trying to locate. It can be a little more complex for a fraction such as 4/15. Again, this is close to a fraction that we might be able to recognize. 15 is close to 16, and 4/16 is 1/4. So we know that our fraction will be pretty close to 1/4, which is equal to 4/16. But now in this case, you'll notice that our benchmark has a different denominator than the number that we're trying to locate, but the numerators are the same. Now the question is, which is larger, 4/15 or 4/16? Well, going back to our definition, we know that if we broke the unit segment into 15 parts, those units would be larger than if we broke the unit segment into 16 parts. Since we have 4 of those parts, 4/15ths, would be larger than 4/16ths. Once again, we need to decide by how much. The answer to that question is going to be pretty difficult to find, maybe not difficult, but tedious at least, using a number line. So we'll save that for another time when we talk more about the abstract and symbolic methods of comparing fractions. Finally, let's talk about placing improper fractions on a number line. We haven't used that word yet. Most of the time when people are talking about fractions, they're talking about numbers that are less than 1. However, as we saw with the definition, we can also represent numbers that are larger than 1 using fractions. 5/4, 6/4, 7/4, 8/4, and so on. Numbers where the numerator is larger than the denominator are called improper fractions. Let's try a simple one first. 13/5, for example. We can use our definition of fractions. Since we're working with fifth, we'll break the unit segment into 5 equally spaced pieces and continue on past 1 and past 2. And then we can simply count 13 of those segments to the right of 0. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and there's our result. 13/5 is right here. But there's a simpler way, of course, and that is to notice that since we're working with fifths, each set of 5/5 represents one whole. So the fraction 13/5 represents 2 sets of 5, 1, 2, plus 3 left over. You may notice that we've essentially determined how many times 5 goes into 13 and kept track of the remainder, 3. The result is often represented as the mixed number 2 and 3/5. So, for the purposes of locating this number, instead of starting at 0 and counting 13, we can start at 2 and simply count the remainder, 3, and we'll get to our number 13/5. We can verify this from our knowledge of fractions by remembering that 2 is equal to 10/5, 2 sets of 5, and if we count 3 more over, we get to our number 13/5. So what about more complicated numbers? Something like 1243 over 165. Well, now clearly a number line is going to be insufficient, and we'll make use of our understanding of the more abstract concepts as we move into these kinds of numbers. First of all, we'll need to find out what whole number is this fraction slightly larger than. So we'll need to know how many times does 165 go into 1243. Well, students are likely to use trial and error here. Let's look, and we can see quickly that it's 165 does not go in 10 times. That would be 1650 is 165 times 10. Let's try maybe 8. 165 times 8, 40, carry a 4, 48, 52, carry a 5. 1 times 8 is 8. That's 13, 20, still a little too big. So we can try 7. 165 times 7, 35, carry 3, 42, 45, carry the 4, 1 times 7, and we get 1155. So we know that we have 7 whole units, and the remainder is 1243 minus 1155. which is, looks like 88. So what we're looking for is 7 and 88 out of 165. So now we can use our benchmark idea. We know that 88 165ths is kind of close to a half. So half of 165 is 82 and a half 165ths. That's a half, and 88 is going to be greater than that. So if we make our number line from 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7, 0 to 8 actually. Here's 7 and a half. 7. Our fraction is going to be a little bit larger than that, and it's just a little bit larger than 7 and a half, only 5 and a half 165ths. So right about there, hardly bigger at all, is where 1243 165ths will be located on the number line. So you'll notice that working with these numbers and trying to locate them on a number line introduces ideas about mixed numbers, improper fractions, and it's a core idea for students to understand. It's very important that they understand that a fraction is a number, first and foremost. In future sessions, we'll talk about other ideas that fractions can represent, but for now, let's look at some assessment questions that will help you to understand further the ideas that we've introduced in this lesson.